Welcome to the Mobilize and Restore webinar series, and thanks to those that have continued on from the research talk. In this portion of the webinar, Stenum will walk the audience through all the steps needed to execute their workflow for video-based clinical gait analysis and provide perspectives on best practices for getting optimal results. And again, we'll take more questions at the end of the tutorial, and please ask those questions in the Q&A panel, and feel free to enter them as Ian's talking. So with that, Ian, please feel free to go ahead and start the tutorial.
Thank you, Matthew, and thanks for inviting us here today. I'm going to go into more detail about the steps from recording a video, setting up a capture space, analyzing the video via OpenPose, and then last, running workflows that we have created in MATLAB for either the sagittal or the frontal view videos. This is a distillation of a document that is posted on the GitHub repository for these projects right here. And so if you're interested, you can refer to that for more detailed information. So the recording would look like panel A here in the left, where a person walks on a walkway shown here by the red line on the floor. And there are two tablets in this example mounted on tripods that record either a frontal view of the person or a sagittal view, as shown here in panel B. In order to set up this space, there are some distances of the capture space that you would need as input to the workflows later on. So for the sagittal plane workflow, in order to dimensionalize the pixel distances into unit distances, you can, for example, use the distance of the walkway, so the length between two strips of tape, as long as it's in the line of progression of the person walking. For the frontal plane workflow, you would need the distance from the camera to either the start or the end of the walking trial, as shown by one of these two arrows down here. In order to take the video and analyze it with OpenPose, in a very rudimentary sort of summary of that, you would take it as input the video that you had just recorded, and the output you would get is the video where the key points have been overlaid as shown by this colored skeleton, and so-called JSON files for all of the frames in the video. These JSON files, they contain the XY coordinates of the various key points, and there is one file for each of the frames. For more detailed information about how to run OpenPose, you can refer to the GitHub repository of the team that have developed OpenPose out of Carnegie Mellon University. We use the demo that they have posted, and after you install OpenPose, you can run it locally on your own computer if you have a GPU, so that you have acceptable processing times. And so you could run it either from your command prompt or a Jupyter notebook. If HIPAA compliance is not a concern, so that would be, keeping videos with identifiable information, that's really not a concern for you. You can also use a cloud service such as Google Colab, which lets you connect to remote GPUs. There are various flags in OpenPose to let you set the ranges of the frames that you want to analyze, and you can refer to the documentation at the GitHub repository for more information for that. The last step here is two different MATLAB workflows that we have developed. I should say that they are independent, so you don't need both videos to run this analysis. They both take as input the output from OpenPose. So that would be the video with the skeleton overlaid, plus all of the JSON files. And then there are a series of semi-automated steps. And I'm going to show two examples of running that. The output is spatial temporal gait parameters, and for the sagittal workflow, 2D joint kinematics. So I am going to shift gears here and pull up MATLAB and run through an example of first the sagittal plane workflow and the frontal plane workflow after that. So you can go to the GitHub repository that we have made and download all the MATLAB files associated with either workflow. This is the sagittal plane workflow, and what you would need to run is the script called OpenPose Gait analysis _SAG. When you run that, a prompt will open for you to select the video outputted by OpenPose, and next another prompt for you to select the JSON files associated with that video. It first asks the walking direction of the person. We need to know that in order to calculate correct gait parameters. In this instance, the person is walking right to left, so we can go ahead and click yes. And the next screen that pops up here concerns left-right limb identification errors that OpenPose may have made. So what we should focus on is this plot right here, which shows the horizontal position of the left and right ankle key points. And so generally we see this alternating pattern associated with the gait cycle and an increase in the values as the person walks across the screen. What we're looking for to correct are instances like this one here and these ones here where we can see something has been flipped. If you click on one of these frames, the image will update to show the image associated with this frame right here. And what we can see is that the left limb has been incorrectly identified on the right. And so in order to correct that, there are various buttons down here. And for an example like this, you would click the delete left ID button. And when you do that, the image will update over here. If we go to the next instance where something is amiss, in this instance, the right leg has been incorrectly identified on the left limb. And so we click the button delete right ID. We move to the next frame. Here, the two key points have been switched. And so in order to correct that, we click the button here, switch left right ID of legs, and it updates the curve over here. These two frames have been switched as well. I'm going to go ahead and correct these. And then the last one is this frame that also has been switched. Now we can see we don't have these switched IDs, and the curve looks smoother. When we are finished here, we can go ahead and click Save. And the next window that opens up deals with detecting gait events of the stride cycle. So what is plotted here is the horizontal distance between ankle key points relative to the pelvis. And so we see this alternating pattern. The positive peaks would be associated with left or right heel strikes, and the negative peaks would be left or right toe-offs. Here at the beginning and end of the trial, we have spurious events. In order to get rid of those, we use the highlight tool in order to select them. And then we click the buttons saying delete events, which will get rid of the spurious events in the beginning. And we can do the same thing at the end and click delete events in order to get rid of those. If we need to create heel strikes, we can also heel strike or throw off. There's also buttons to do that. If you're working with a long file with a lot of gait events, it can be a little bit tricky to visually pick them out. So in order to aid that, if you click the summary button right here, that will create a plot of the gait cycles overlaid. And it's a little bit easier to pick out if there's anything, if there still are spurious events. What we're looking to see is something like this, where we have this repeating pattern with some level of variability from stride to stride. When we're finished picking out the events, we can go ahead and click Save, and that will take us to the last step of the workflow, which is dimensionalizing the pixel distance into a unit distance. We use the distance, in this example right here, between two strips of tape on the floor, starting here, going to here, and we know that that distance as input here is 6.3 meters. We calculate the scaling, which calculates a scaling factor relating pixel distance to unit distance. And once we are finished, we can go ahead and click Save, which is the last step of the workflow. What this creates is a MATLAB mat file saved in the folder that contains your video. That includes the output parameters of the workflow. So next, I'm going to show the steps for the frontal plane workflow. So you would navigate to a folder with all the MATLAB files. For the frontal plane workflow, you would need to run the script called OpenPose Gait Analysis _front. And like before, there is a prompt for you to select the output video from OpenPose and the associated JSON files. It first asks you the walking direction of the frontal plane video. In this example right here, we're analyzing a video where the person walks away from the camera as opposed to an example where the person walks toward the camera. We click away, and that will take us to a window like so. That again deals with any errors in left-right identification that OpenPose may have made. Now I should say that that is not as common as a problem for these frontal plane videos, but we have included it for completeness. The graph here shows left and right shoulder and ankle key points. You can see that the plot sort of narrows as the person walks away from the camera, and so they appear smaller in the image. This example looks good. There are no errors. If you would encounter an error, it would look like so, where the key points have been switched for a particular or multiple frames. I'm going to go ahead and revert that. And when we are happy that there are no errors or they have been corrected, we can go ahead and click Save, which will pull up the next window dealing with gait cycle detections. So what is plotted here is the vertical distance between the ankle key points. And we see this alternating pattern that becomes smaller as the person walks away from the camera. We have found that we can use the positive and negative peaks to detect gait cycle events, such that the positive peaks would be associated with left heel strikes and negative peaks with right heel strikes. In order to get rid of spurious events, as shown here at the end, we can use the brush tool and then the delete button right here in order to delete those. And we can also create heel strikes if we need to do that. Once we have finished this step, we can go ahead and click Save, and that will pull up the last step of the frontal plane workflow, which is inputting the distance from the person to the camera at for example, here, at the beginning of the gait trial. In this example, we know that the person was 2.33 meters away from the camera here at the beginning. And so when we click the push button right here, what it'll do is that it'll calculate a time series of depth of the person relative to the camera for the entire trial, from which we can get parameters such as step length and gait speed. This is the last step of the workflow, and we will get a MATLAB file that is saved in the folder containing the video that has the output of the analysis. I'm going to go back into the presentation in order to wrap up. And so the outputs that you get for the sagittal workflow would be various spatial temporal gait parameters such as gait speed, step time, step length, stance time, swing time, double support time, and sagittal plane joint kinematics of the lower limb, left and right, hip, knee, and ankle angles. For the frontal plane workflow, we get a more limited set of spatial temporal gait parameters, gait speed, step time, and step length. So what you would need in order to run an analysis like this would be a tablet or a smartphone, ideally mounted on tripods. You would need a tape measure and some tape to mark the floor in order to get these parameters needed as input for the workflows, and a computer to run OpenPose and MATLAB. If you have any questions, I'll be happy to take them now. You can also get in touch with me offline or post any issues to the GitHub repository. Thanks.
Okay, great. Thanks, Jan, for the clear tutorial. We'll hop back to questions now. And just a heads up, we'll try to respect time. And it looks like Ryan's already answering some questions. And any questions that we don't get to during the webinar, we can answer after the fact. And we'll post them in a Q&A document on our website and also share them with all registrants. So just going back to the questions, a question from Andreas Bortanis. Have you thought about trying to calculate three-dimensional movement from the single views in either case, or maybe combining the two cameras together?
At this stage, we've thought about it, but it's not something that we have pursued so far. Obviously, if you're using multiple cameras, there's an issue with syncing, and you would certainly require a little bit more on the hardware side in order to run that analysis.
Yep. Great. A question from Saeed Forghani, and I think this maybe just is a question about obviously the method requires like a forward progression, or does it require a forward progression of movement in order to calculate these parameters? The question was centered around using this method in someone doing treadmill walking. Maybe you want to get some of these spatial temporal.
Yeah, that's a good question. For the sagittal workflow, it is not a requirement because we would still be able to get step lengths and from that. For the frontal plane workflow, that would be an issue because everything is based, or all the spatial parameters are based off of the size of the person, and if that's not changing on the treadmill, we can't. We need that translation in space in order to get those parameters. So that wouldn't fly with treadmill walking, but the sagittal workflow, that will work.
Yeah, great. A question from Felipe Fernandez Gonzalez. Have you considered trying to calculate kinetics from the motion as well, not just spatial temporal parameters?
Short answer, no. I mean, that would be great, and with something that we have also thought about, but haven't really dipped our toes too much into this side of things. We have a data set with treadmill walking and ground reaction forces, so it's something that would be very informative if we can get good measures of that as well.
A question from Maria Isabel Veras Orselli. Can we improve the lower limb side identification by using something like identifying the limbs in some way, maybe with markers on the legs, or
Yeah, I think
thoughts about improving the models, or things like
I
that?
think this is sort of a general observation about what I've just presented. I think there's potential for automating a lot of these steps here. We have sort of chosen this path for, not necessarily computational efficiency, but more working very closely to the data. And there is, I think there's big potential for automating a lot of these things to improve that. But sort of our we've sort of weighed the pros and cons is that we would want to work very close to the data, and then taking this initial approach.
Yep. A question from Lauren Gruss. So have you worked on, or have you considered integrating the kinematic data with any simultaneous force plate data? Or maybe you could speak to if people are trying to maybe synchronize some of these parameters with other sensors are trying to collect at the same time. And this can be a question from both Ryan and Yana. Yeah.
Did you have a comment, Ryan? Like,
say that again, Matt. Sorry, I was in the questions in the chat.
Oh, it's okay. The question is, have you considered integrating the kinematic data with other simultaneous data like force plate data? Or
oh yeah. So this is related to a question in the chat too. Somebody had asked about treadmill data. We have instrumented treadmill video. We have force plate treadmill data and simultaneous video data. Haven't tried to integrate it yet, but we have that data set. I would point, if people are interested in that kind of thing, I would point them to OpenCap, which I know there's already a discussion going on in the Q&A about OpenCap, but that's really kind of, one of the strengths of OpenCap is that you can start to predict these kinds of things with the video data.
Yep. Okay, great. So let's say, Ryan, you've been answering several of the questions, and some of them are related. And again, we can answer these after the fact. So we can, I think, go ahead and close. So again, thank you, Ryan and Yen, for a great talk and tutorial. And thanks for everyone for the great questions. Please be sure to click on the link that will appear at the conclusion of the webinar and take our survey. That'll help us improve the webinar series and choose upcoming topics. Again, this webinar series is supported by 2 grants from the NIH, including the grants that support our Mobilize and Restore centers. We're grateful for the support which allows us to run these webinars and other events. And we want to thank everyone for participating today. We hope you continue to stay involved with our centers, and that we will see you in a future webinar. Thanks, and have a great day.